Okay, let us see now some examples about the use and calculation of the directional derivative. Okay, the first one is a direct one. Let f of xy be x squared plus 2y squared. Question is to find d I plus j of f at the point, say, 1, 1. Okay. Well, firstly, we observe, because it's a short way of calculation, we observe that f is differentiable everywhere. Okay, this is because its partial derivatives are continuous. By the fundamental lemma, we get this. So, very simply then, d I plus j of f at 1, 1 is nothing but the gradient of f at 1, 1. Just this. Okay. Dot I plus j. But we have to be careful. In this short way of calculation, in the presence of the differentiability, we have to use here the unit vector. Well, this is the vector 1, 1, so its length is root 2. Well, the rest is then direct calculation. You have 2x and 4y at 1, 1 dot 1, 1 divided by root 2, which is, of course, 2 plus 4 over root 2. Okay. So this was a direct calculation. I wanted to emphasize that in this formula we have to use a unit vector all the time. Okay, a differently phrased problem. Find the rate of change of the function 2xy plus x squared if p moves from p0, which is given here as 1, 2, towards p1, which is 1, 1. Well, first of all, the rate of change of a function, meaning that, of course, the instantaneous rate of change of a function in a certain direction means directly the derivative in that direction. So this is the directional derivative. Okay. So dvf at p0 is wanted. Okay. The only thing which is not very clear here is what is our direction? Well, the direction is from p0 towards p1. And the direction v is from p0 towards p1. And therefore, it is p1 minus p0, so that is 0 minus 1. Well, secondly, the function is a polynomial, so it is differentiable. So it is differentiable everywhere. And thus d of 0, minus 1, that is in the direction. This is our v. F at the point 1, 2, which is our P0, is gradient f at 1, 2, dot the unit vector in this direction, but it's already a unit vector, so it's just 0, minus 1. Okay. And this, of course, is looking at our function. It is y plus 2x, and the derivative with respect to, wait a minute, with respect to x, that's 2y plus 2x. And with respect to y, it becomes just 2x. Okay. So at the given point, okay, x is 1, y is 2, so that's 6, and 2 dot 0, minus 1, so it is minus 2. Okay. Well, a third example would be assuming f is differentiable at P0, which is given as, it's not given, at some P0, and, okay, given that the vector in the direction of I plus j of f at P0 is 1, and the length of the gradient of f at P0 is square root of 2, find all possible values of fx at P0, fy at P0. Okay. Well, now, let us use what is given to us. Actually, there are three things given. F is differentiable, a certain directional derivative is given, and the length of the gradient is given, all at P0. Now, differentiability tells us that the directional derivative in the direction I plus j is f sub x at P0, f sub y at P0, dot the unit vector, which is, as before, 1, 1 divided by root 2. And that is given to be 1. Well, that tells us that f sub x at P0 plus f sub y at P0, taking the dot product, is square root of 2. The other one is a norm, the length of the vector. So it tells us that fx at P0 squared plus fy at P0 squared, okay, is equal to square root 2 squared. Now, using these two pieces of data, we get the following. Of course, from the first one, squaring, we get f sub x at P0 squared, f sub y at P0 squared, plus twice f sub x, f sub y, okay, that's the square here, is equal to 2. Now the second one says the sum of the squares is 2. So fx, fy is 0. Well, this tells us directly. So f sub x at p0, rather, this can be 0. Then, of course, from the first equation, we see that the other one must be square root of 2. And similarly, if f sub y is 0, then f sub x at p0 must be square root of 2. So these are the only possibilities. Here we made use of differentiability, actually. This is the third example. Okay. Now, right, let us see an example where we can make use of the directional derivative. Okay, assume the only force is gravity, meaning there is no friction and other problems concerned with it. A ball is put at P0 on the surface. Of course, the ball is not a large physical ball, it's a point. You can think about it that way. On this surface, f of xy, z is f of xy, which happens to be xy minus 2x squared. Okay. So A, if P0 is the point 0, 1, 0, on the surface, well, that's clear. If x is 0 and y is 1, z clearly will be 0. Then, in which direction will the ball move or roll down? Of course, our logic, common sense, tells us that it will move in the direction where the slope is steepest and downwards. Okay, because this is a continuous surface. Okay. So obviously, in the direction where the slope is steepest downwards. Now here, let me make a short comment. What is the geometry here? It's the following. Okay, we have a surface, think of it as a hill perhaps. At some point in it, that is our P0, okay, we put a ball. Okay, where will it roll? Of course, it will roll down in this direction. Okay, it will not go up under gravity, so it will fall there, or it will not move on a horizontal path. It will fall down, okay, in the direction where we have the steepest slope. What is the direction wanted? Well, the direction is not this direction. Namely, how do we measure direction? Okay. Well, by an instrument called a compass. On the compass, we have north, south, west, east, and it is a horizontal instrument. Namely, it is two-dimensional. Okay. The actual slope is like this, but, okay, you don't say you go down and then up, you say you go west. That is the direction you go. So, the direction then is the following. The man holds a compass, which is horizontal, and you have here north, south, east, and west. And there is a direction here, which must be, okay, the direction the needle shows. So the direction is horizontal. It's perhaps something like this. This is the V wanted. Okay, V is planar. It's on the plane. It's horizontal. Okay. But actual slope where the ball will fall is dVF at P0. Okay. The direction is horizontal, okay, but the ball will fall in this direction. Why is it horizontal? Because the direction vector V is an xy plane. It tells us how P moves, okay, at the bottom. Okay, so it's horizontal, and so this is the picture roughly. Well, so the question is, okay, find the direction V where this actual slope is steepest. So the question becomes, okay, find V such that dVF at P0 is most negative, i.e. where it is minimum. So where is it minimum? Well, we can calculate this, of course. Now, we immediately see that in calculating this directional derivative, that f is differentiable. It's a polynomial. Okay. So dVF at P0, I will not bother with vectors with a non-unit norm. So I will simply say it is cosine alpha sine alpha. So it's a unit vector. This is gradient of f at P0 dot cosine alpha sine alpha. We want this to be minimum. Okay, what's the variable? The variable, of course, is v, the direction. We are looking for the direction, but that means alpha. So here, this is a constant. Okay, this does not depend on alpha. And alpha is the only variable. Let us calculate this vector now. Our f is given to be xy minus 2x squared y. So gradient f at P0 is the derivative with respect to x, so y minus 4xy. And x minus 2x squared. That's derivative with respect to y. and the other one is derivative with respect to x. But at the point which is 0, 1. The other one, the third one, tells us the height. We are not interested in the height right now. So that would be, okay, x being 0, the second one is clearly 0, and y is 1. So this is the gradient vector at this point. So dvf at p0 becomes 1 times cosine alpha plus 0 times sine alpha. So it is nothing but cosine alpha. Clearly, this is minimum. If alpha is positive. The minimum value of cosine function is -1, so it is this. What does this mean? Remember, here alpha was the angle from the x-axis. So this vector is minus I vector. In other words, it's the west direction. Okay? In the compass. In this direction, okay, we have the most negative slope, and it tells us that the ball will fall in that direction. Okay. Now, secondly, okay, the same question with a different P0. It is now 1/2 0, 0. Now, y is 0 now, so z is 0, x is 1/2. It's a point on the surface. Okay, so we look at dv f at p0. I will not calculate it again. I did over there. It is y minus 4xy. Okay, my y is 0, so the first is 0. And the second one, x is 1/2, but that means it's also 0. Now, what does this tell us? That's to say, of course, this is the gradient of f at p0. Dot, we have to take the dot product. Okay, so which value of alpha makes this most negative? Well, none. They're always 0. This is 0 for all directions. Okay. Since this is the change in the instantaneous change in the function in a certain direction, if in any direction you have a 0 slope, it means that all tangent planes there are horizontal. Well, this means, so tangent plane is horizontal at this p0, so ball does not move. Okay. Now, this does not mean it is in a very comfortable, stable position. It can be at the very top of a hill on the surface, or it can be at the bottom of a ditch, which is a stable equilibrium. Whatever the case, The tangent plane is horizontal, so the ball does not move. Now, a remark is appropriate here. If f is differentiable at p0, then it is easy to calculate the direction v, okay, such that dvf at p0 is minimum or maximum. Why? Because of the following. Okay. Let us look at this differentiability again, because then dvf at p0, okay, will be f sub x, f sub y at p0 dot, okay, this is just a gradient vector, dot cosine alpha sine alpha. This is the unit vector v. Unit vector in direction of v. Well, this is a dot product. Okay. Dot product means that, okay, it is the length of gradient f at p0 times the length of cosine alpha sine alpha. Well, these are vectors, after all, and we have a dot product. So it's the product of the norms times cosine of the angle between them, of the smaller angle between them. So let me write cosine beta. Here, beta is the smaller angle between the vectors gradient f at p0 and v, because this is v. It's in the direction of v. So the angle between them, if we take the cosine, that becomes the angle beta. Now, let us recall what we were looking for. We are looking for the smallest and the biggest values of this expression when alpha changes. Alpha is the only variable. Okay. But here, okay, we get, let me just go one step further, gradient f at p0 times 1 times cosine beta, because cosine alpha, cosine alpha vector is a unit vector. Its length is 1. So here we want to minimize, maximize when alpha changes. Well, we don't have any alphas in here. It's a gradient of f. It has nothing to do with the direction. But here, beta is the angle between the alpha direction and the gradient. So in beta, we have alphas. It depends on alpha. Okay? Beta changes. So when the question is, when beta changes, minimize and maximize this. Well, clearly, cosine beta is minimum. It's -1. If beta is pi, so if beta is pi, okay, cosine beta is minimum. And if beta is 0, cosine beta is maximum. Okay, so conclusion. dvf at p0 is minimum if V is, okay, equal to, if V is in the, makes an angle pi with the gradient vector. That's to say, if, okay, let me say, the vector V, okay, makes an angle pi with gradient f at P0. That is, they're oppositely directed. V is minus gradient f at P0. And is maximum if the same question, okay, V is gradient f at P0, because the angle between them is 0 now. So I can take V as the direction of the gradient. So this conclusion says that if f is differentiable, that is, that's the basic thing here. If f is differentiable so that we can use this formula, the largest value of the directional derivative occurs, okay, if we take the derivative in the direction of gradient f. Okay, note that this is a two-dimensional gradient. Okay. So we are in the plane. And in the opposite direction, we have the smallest slope, the most negative slope. Well, this is again understandable, because if you are on a hill somewhere, and at some point P0, this is the most negative slope, well, you have a tangent line, so go the other direction. It's the most positive slope. It's the negative of the other one. So, if this is, okay, the most negative slope direction, then this is, well, let me say here, this is the most, okay, positive slope direction. They are opposites of each other, as we would expect. The next example is an important one in the sense that it tells us that this short way of calculating the directional derivative is not always correct if we don't have differentiability. So, okay, let fxy be, well, this is an example we encountered before. Okay. So this is our function. It's defined everywhere. Okay. Well, now this serves as a counterexample, as we will conclude at the end. Let us find directional derivatives in all directions. Okay, I will put a unit vector at the point 0, 0. Okay. I will not attempt to use this dot product version because, okay, We are not sure f is differentiable because there's division by 0. It's complicated. Actually, it is not differentiable, as we will see a minute later. Now, this is then the limit t goes to 0. F of x0 t cosine alpha, y0 t sine alpha, minus f of 0, 0 divided by t. This is the definition of the directional derivative. Well, f of 0, 0 is 0. It's given. And we can simplify this by substituting the values. Now, x is t cosine alpha. That's just 1, power 1. And we have t sine alpha squared divided by x squared plus t to the 4th sine to the 4th alpha divided by t. Now we want to evaluate this limit. Well, you can easily see a few things. First of all, there are basically two cases, so I will separate them. Now, if cosine alpha is 0, it may happen that cosine alpha is 0. Then sine alpha is not 0. They cannot both be 0. So this says that I have t to the 5th divided by t to the 5th, but I have cosine alpha 0. So this is 0 divided by this. In other words, it's the limit t going to 0, 0 divided by t to the 4th sine to the 4th of alpha, which is, of course, 0. Because the bottom goes to 0, but the top is not going to 0. It is equal to 0. Just you put the 0, you take the limit of 0. Now, if not, if cosine alpha is not 0, then, I can cancel t squared by taking it out. So we get t to the 3rd power at the top. At the bottom, I have t cubed again. So canceling those, we have the limit t going to 0 of cosine alpha sine squared alpha divided by, this is t cubed. I have t squared t cubed. I have cosine squared alpha plus t to the 5th at the bottom, so it becomes t squared sine alpha. This, of course, is when t goes to 0, this is a plus sign. When t goes to 0, it is sine squared alpha over cosine alpha, because cosine alpha is not 0. Well, this tells us that whatever the direction is, this function has a directional derivative in all directions. Not only partial derivatives, but in all directions, it exists. Okay. Whatever alpha is. But f is not differentiable. Because if it were, f would be continuous. Of course, differentiable at 0, 0. I mean, everything happens at 0, 0 here. Would be continuous at 0, 0. okay? But we showed before that limit f this limit does not exist. Because there is no limit, it cannot be continuous. If it's not continuous, it cannot be differentiable. Differentiability was much stronger than continuity. It implied continuity. So, okay, it's not differentiable. Well, just check. The gradient of f at 0, 0 dot, okay, cosine alpha sine alpha. Okay. This is a unit vector in the alpha direction. Okay, assume cosine alpha is not 0. Or let me just write it down. Well, this is f sub x, f sub y at 0, 0. Now, what is this? Let us just calculate that here very simply. This is the limit t going to 0, f of, well, x is the variable, so y is constant, and 0, x is the variable, minus f 0, 0, divided by x, so x goes to 0, sorry. Well, x minus 0 here, so we have this. Well, f0, 0 is 0. What is fx0? Okay. If you look at the function, you have y squared at the top. X is not 0, but y is. So this is directly 0. Which means that this limit is 0. Similarly, f sub y at 0, 0 is 0. So putting these in place, we have 0, 0 dot cosine alpha sine alpha, which is 0. It is not the directional derivative of f at 0, 0 when cosine alpha is not 0. Because if it's not 0, we found it to be sine square alpha divided by cosine alpha, which is not 0 in general. But here, it says it is 0. Okay. Well, of course, sine alpha must be not equal to 0. Let me write that. So in some alphas where both are non-zero, cosine and sine, this does not give us the directional derivative. Okay? Well, the reason, as we just mentioned here, is that f is not differentiable. This short way of evaluating directional derivative using the dot product is not correct if f is not differentiable. Well, at least it's not guaranteed. So we cannot use it. Okay. Well, the last example in this matter, a rather fancy example. For short, that's my sixth example, right? Okay. Well, a factory produces 200 items and sells for the price sells, okay, let me say each item, for this price. Okay. Of course, this is a big company, and okay, the production or the price cannot be immediately changed, but slowly. Okay, you need some preparations and investments, etc., etc. Okay, and there are mathematicians hired by this company, and okay, the profit function happens to be, okay, let me say I put P first, so let me do it this way. It depends on the price and the quantity produced, okay? And it happens to be QP minus Q squared over 4P minus P to the fourth over 8. Okay, now, this is a hypothetical example, of course. It roughly says the following. If you produce a lot, of course, there will be a big cost, and you will lose money. If you increase the price very high, you cannot sell your products, nobody will buy them, so you will go bankrupt, because you have the fourth power, which increases very fast. So you must have a balance between them. Okay. Well, it can be calculated that at this level of production, this happens to be, you can calculate that, minus 250, which means factory loses, or the company loses money. So something must be done immediately, but you cannot jump from, okay, a price to another one or a production level to another one immediately. So what's the, you can only move in small steps. Okay. Since P or Q cannot be changed immediately, okay, cannot be changed immediately, okay, we have to go in steps. Namely, small changes are possible. So what should be done? Okay. Well, the idea, of course, is to go in the direction where the rate of change of the function is most positive. So you will move a little step, but it must be in the direction where the function will increase most. Okay. So the production levels and price, of course, must be adjusted, okay, such that the function, okay, moves, okay, to higher values, okay, in the fastest way. Of course, mathematically, this means that in the direction such that dVf at this production level, okay, is most positive. Okay. So you will change something very little and you will move the profit in the most positive way. Okay. This, of course, since the function, since f is differentiable at p0, not at 0, 0, but at p0, okay, this means v must be taken as gradient f at p0, because this is the direction that gives you the most rapid increase in the function. It's the steepest slope. And this direction gives that slope. So, what is f sub 1? Okay. Well, this is the derivative with respect to p. So that happens to be q plus q squared over 4p squared and minus 4p cubed over 8, differentiating with respect to p, and del f del q, that is f2, okay, would be p minus 2q divided by 4p, okay, and all evaluated at p0. So, the gradient f at p0 happens to be, okay, I had calculated that somewhere, so that should be, oh, here, okay, minus 200 SB. So what does this tell? This says that, so, okay, if we move in this direction, it means that q must not change because it's already 0. You don't have to change it. You must go in that direction. So that is 200 times minus r. So this is the direction you have to move. You have to decrease price. So p must move in minus r direction, i.e. p must be lower. Okay. Say p goes from 10 to 9, then f9 200 would be minus 131. So you made a huge profit, you decreased your cost, and your profit increased from minus 250 to minus 131. This is still not good, of course. Your company loses money, but this is the first step you must take. Okay. So B, the second question, okay, what is the ultimate goal? Okay, of course, it's to maximize f. Okay. The answer is easy. To, okay, maximize f in the long run. Okay, where do you maximize it? Is there a maximum? Well, these are the questions you must ask, but of course, it's easy to check that. I will not go into that in detail here, because clearly when p goes to 0, okay, this function tells us that the profit goes to minus infinity. So there is no minimum. I mean, you can make a loss as big as you want. Of course, you don't want it. So, okay, find critical points. This is, it happens. It's easy to find them. I will not go into that. That P0, that is 6 and 72, okay, is a critical point. Okay. And it gives maximum of f. And f of 672 is 54, and finally you have a positive profit. Okay. But there's a long way to go there. The immediate step is in the direction of the directional derivative.